let's continue on here. What does this do with potential? This term. This term right here. If I increase the potential, first of all, what's 1 minus alpha? What's usually this term going to be about? What's alpha usually?
Half.
Roughly a half, right? So 1 minus alpha is a half, and alpha is a half. So as I increase E, what happens to this term? So if E goes more positive, what happens to this term? Increases in what way? Linearly or exponentially, right? Okay, so this is going to kind of be exponentially increasing, right? Can it exponentially increase forever? Can this oxidation current increase exponentially forever?
No, because concentration will come to 0.
Because CR at the surface will go to 0, and then you'll get a mass transfer limited current, right? So this term, has sort of an exponent, but that exponent's going to be modulated by the fact that it's going to hit a limited current, right? Okay. And so it's the same for this term, the reductive current. So as if E gets very large and negative, right? E has to be negative to pass a cathodic current. E is going to be E minus EEQ is negative anyways, a negative overpotential. Negative times negative is a positive, so this is going to, again, get up very large. Okay, so let's think about what this looks like. So we could have a plot here, just give a sense. Then I could draw the cathodic current. This is going to be I over IL. I'm going to plot I over IL, so a relative current, or a normalized current, versus eta equals E minus EEQ. So this is the deviation from equilibrium. And I can think about each term, right? I can think about the cathodic term, and I can think about the anodic term. Okay. And this is Barton-Faulkner notation, so cathodic currents are positive, whatever, don't worry too much about the sign. So this is going to increase exponentially until you hit some plateau. Increase exponentially until you hit some plateau, right? There's my cathodic term. And my anodic term is going to be this, okay? And this is going to be equal to I naught, right? This is going to be equal to I naught, the magnitude, right? And the total current, well, what's the total current at eta equals 0? The cathodic current plus the anodic current is equal to what at eta equals 0? 0. So I can put this curve here, right? And so basically, I'm going to have a curve that goes through like this, like that, right? So that's my total current. I total. This is IC, and this is IA, right? And so you can see if I have a very negative applied potential, then it's purely cathodic current I'm worrying about. This term goes to 0. This term is very small, right? So if this number is very negative, you have E to a large negative number. What's that?
0.
Goes to 0, right? E to the negative infinity would be 0. 1 over E to the infinity is 0. So this goes to 0. So as you get to very large potentials, this term goes away. Large negative potentials. Large positive potentials, the other term goes away. And then it's in the middle where you have to add both terms up, and then where they cancel out at equilibrium. So just so for your notes, for very positive E, IC goes to 0. For very negative E, IA goes to 0. And IL is the limiting current, which we have already talked about in one case earlier. And that's the max current mass transport can deliver. So that's it. That's a conceptual understanding of Butler-Volmer kinetics with mass transfer involved. we'll go to some special cases now that you often encounter in the literature, and we'll try to express the mass transfer limiting current in a different way that's a little bit more useful and connected to what you learned in chapter 1. So this is approximate forms of the IE curves, I guess. I could call it I eta, current overpotential. So A, no mass transfer limit. So one way to think about that is imagine I have a solution and I'm stirring really, really fast, okay? And all I'm doing is passing just a little teeny bit of current, like a nanoamp of current. Do you expect this concentration to be different than this concentration?
No.
No. I'm stirring really fast, so my diffusion layer is really small, thin. I need to pass a nanoamp, but that requires this to be infinitesimally, well, not infinitesimal, but it requires it to be very, very, very little different than that to pass that current. So for all effective purposes, this ratio is maintained at 1. So in the limit of small currents or of really fast mass transfer, we can write that I equals I naught e to the negative alpha f eta minus e to the 1 minus alpha f eta. Okay, now it's getting more manageable, right? There it is. So that's the no mass transfer limit. And you see this a lot. For example, if you're doing hydrogen evolution on a platinum electrode in 1 molar acid, you don't see much mass transfer limit from the protons. Because you have a lot of protons around, and they diffuse very fast. So the limiting currents are very high for protons. And you get this because CO 0T is equal to CO star, and CR 0T is equal to CR star. And this is a good approximation when I is less than IL over 10. So when I is about 10% or less of the limiting current, it's a pretty good approximation. You don't affect the surface concentration much relative to the bulk. And you can use this equation. And we say the curves that we get are dominated by activation over potential. And so, for example, I could draw some curves, and this is going to be eta in volts, and this is going to be, say, J, current density. And you have to do this for the lab, but you might see basically exponential behavior, and then it goes to 0 here. So it's exponent in both directions, and this might be, say, J naught equals 10 to the negative 3 amps per centimeter squared. So that's a relatively big J naught. This might be, like 0.1, 0.1 volts or something like that. And then if you have a small J naught, what's going to happen if J naught's small? By the way, what's the difference between J naught and I naught? Current density versus current. So I is current, J is usually current density, so current per unit area. It's the only difference. So we just normalize out the A in all the equations, basically. And oftentimes we're interested in current density. Experimentally, I always report current density because you don't want the current to depend on the size of your electrode, which is going to vary from person to person and sample to sample, right? And so what's going to happen if J naught gets much smaller? What's going to happen to the curve? Well, if J naught gets smaller, what's physically happening? Are the kinetics getting faster or slower? Slower. Why? Okay, so at equilibrium, there's less stuff sloshing back and forth, right? At equilibrium. And so that means the standard rate constant is smaller, right? And so the activation barriers are bigger, right? Kind of stepping back through our derivation. So if the kinetics are slower, do you think you're going to need more or less overpotential to get the same current flow? Overpotential is the extra driving force relative to equilibrium. It's kind of how downhill, how much you have to raise that curve to get the reaction to flow at a given rate, right? Remember, at equilibrium, forward and backwards are the same, and there's some hill in between. I raise one side and makes that hill smaller, so stuff starts going one way. And as I keep raising it, I get more and more current, right? Because more and more stuff can get over the hill. And if the hill's bigger, I have to raise it more, right? And so if I have a smaller J naught, it's going to sort of look like that. So this might be J naught equals 10 to the negative 6, amps per centimeter squared. Okay, so that's just an example. You can calculate all these things using the current overpotential equation. Actually, I think you have to do this with the Tafel equation, I think, for the lab, right? Another approximation we can do is small eta. Okay, small eta. So you may know that e to the x is approximately 1 plus x for small x, right? That's like a Taylor expansion, right? Mm-hmm. So that's fine. So it's a linear approximation to the exponential. And so I can write I equals I naught e to negative alpha f eta minus e 1 minus alpha f eta. So that's our current overpotential equation, ignoring mass transport. So assuming mass transport is fast. And then I can plug in this approximation, and I get I naught 1 plus negative alpha f eta, so that's x is that, minus 1 plus 1 minus alpha f eta. And then I can cancel terms out, so the 1's cancel for sure, 1 minus 1, I naught equals negative alpha f eta.
I guess that
plus,
should be minus.
Which one?
Minus what brackets?
Probably, yes. Thank you. And yes, good. Okay, so alpha f eta minus f eta plus alpha f eta, right? And then I get these two terms cancel, and I get I equals I naught f eta. That's pretty cool. So this is basically telling me the current is linear with the overpotential. V equals IR. This is V equals IR for our electrocatalytic reaction. Right? Because this is V. Eta is a voltage from equilibrium. Like if a resistor is at equilibrium, it has the same voltage on both sides, right? I is the current. And this is 1 over the resistance, basically. So we'll write that in a second. And you can kind of see that here. Look, they kind of go through, they're linear. They're linear at small I, right? So this is actually really important when we start talking about impedance analysis. We often assume when we do AC, so with alternating current, we apply an alternating voltage to an electrochemical system. We often assume that different elements of the circuit can be modeled by resistors. And this is why. Because you can model a charge transfer reaction as simply a resistor with some resistance if you only modulate the voltage a little bit. You don't have to worry about the exponential dependence. And it has to be really, because this slope here around 0 is pretty close to linear. And so we call that charge transfer resistance RCT equals 1 over F I naught equals RT over big F I naught. So eta equals RCT times I. D equals IR. So we'll get into impedance analysis later, and we'll model charge transfer as a resistor, and that's why we can do it. Yes, question?
I missed what CT is.
Charge transfer. Okay, so then we can also think about what happens at large eta. Here we have our equation again. What happens when eta is large and positive? Okay, if this is positive, this term will get very large, right? and it's going to be negative a very large term, so it's going to go to negative, this whole term will go to negative infinity, right? And then what happens to this term? Okay. So this term goes to 0, and this term stays around. Or if eta is negative, so if I'm driving a cathodic process, and eta is negative, this term gets really big and this term goes away. Okay? So let's think about the cathodic process. We can get rid of this term. So eta large and negative. This is a cathodic process. Okay? I have I equals I naught e to negative alpha f eta. Right? F eta. Or eta equals RT over alpha f ln I naught minus RT over alpha f ln I. Or eta equals A plus B log I. Okay, so this is the Tafel equation. This is Tafel. This is, now we have a way to evaluate what those Tafel coefficients are, right? Right? I have B and A. Those are my Tafel coefficients, B and A. And now I actually have them in terms of alpha and F. Okay, so in lab, I think in your analysis, you have to make a Tafel plot, right? So historically, in a Tafel plot, how you do this experiment, what you typically do is you apply some current. Let's call it current density. We'll say, amps per centimeter squared. So you'll apply some current density, and then you'll measure eta in volts. So that's kind of how you do it. So that's what we plot the independent variable on the x-axis, which is going to be the log of the current density. Let's say you go from 10 to negative 7, 10 to negative 5, 10 to negative 3, and you might measure eta from 0.1, 0.2, 0.3, 0.4. And if I plotted the Tafel equation, I might be, well, actually my data, well, yeah. If I applied the Tafel equation, it would predict a line like this. Right? Where this x-intercept, what is the x-intercept actually? So if you look at this equation, y equal to 0, what do you get? We're going to extrapolate to eta equals 0. That means we're at the exchange current. So this is actually going to be I naught. Well, in this case, log I naught. But, right? You can see that here. If I set eta equals 0,
Yeah.
I can get rid of these terms. I can divide by these terms. And I get ln I naught equals ln I. So I at eta equals 0 equals I naught. Obviously, right? Go to eta equals 0, you should have I naught. But of course, I thought we said the current was 0 at eta equals 0. Why isn't it 0? Because this is an approximation. What did I do?
You can't use
I
that.
threw away this term.
You can't use that.
Right?
That.
So does this doesn't actually tell me the predicted current at eta equals 0. If I actually went and measured data, my real data would, fall on this curve for some point, but then it would kind of not fall on that curve anymore. And that this is basically where the Tafel equation not valid. Okay? And then if I went to really high currents, it's also not going to fall in that curve because mass transfer resistance important. You see that? Because I can't just keep putting more and more current through the system and expect this equation to describe it, because eventually I won't be able to bring stuff to the surface of the electrode fast enough, right? So what you can do, though, is you can say, okay, well, the Tafel behavior is valid in this region, and then I know the Tafel behavior is described well in this region. I can extrapolate back, and I can get I naught. So I can actually use this linear extrapolation to get the exchange current density. This is how people measure exchange current densities. By using Tafel plots and extrapolating back to what the current would be at 0 overpotential if I only thought about the forward process, or only thought about one of the processes, right? So it's kind of saying, what current would this process give me if I had no driving force? And of course I'm ignoring this side, so the net current is of course 0, but this is sort of a conceptual framework to extract I naught. Okay, and this has the Tafel slope, and the Tafel slope equals RT times 2.3 over alpha F. That's the Tafel slope. The 2.3 comes in from going from ln to log. So this is log, it was ln before, so that's where the 2.3 comes in. Slope equals RT times 2.3 over 0.5 times F for alpha equals 0.5, and that gives us 120 millivolts per decade. So what the per decade means that every time you increase the current by an order of magnitude, you have to apply 120 millivolts extra driving force. So the Tafel slope of a reaction tells you how fast the current increases with driving force. And it's really, can be thought about as it's related to that prefactor that's in the exponential of the Butler-Volmer equation. So the Tafel equation is not valid down here because in the Tafel equation I'm ignoring the reverse process, and the reverse process is not ignorable. Yeah, so if you think about it, it's the slope, right? So it's rise over run, right? So if I want to increase this by 1, which on a log scale, I'm going to be better. You know, this is kind of plotted. I should probably have done this, like -7, -5, -3. That would have been better. Because then if I want to increase this by 1, go from -7 to -6, run, how much rise do I need? Right? And it's saying, well, I need 120 more millivolts. Do that. So it's really important from a practical standpoint because it tells you like how fast is the current increase with applied voltage. Smaller slope is better from a perspective of increasing current with applied potential. Tafel slopes typically range from anywhere from about 20 millivolts per decade up to several hundred millivolts per decade. And then people try to interpret them, and the interpretation is a little bit challenging sometimes. Okay, so I could show you this, but I think I'm going to skip it today. But I'm going to write out the starting point. So I over I naught equals CO of 0t over CO star e to negative f eta minus CO 0t over CO star e to the 1 minus alpha f eta. Okay, so this is the current overpotential equation. What happens for I naught much greater than I? So I over I, or I could also say I over I naught goes to 0. So very fast kinetics. What do you think happens to this equation? What equation should you get back if you have very fast kinetics at your electrode surface? The Nernst equation, right? Because the kinetics are very fast, you should be at locally, you should be at what? Equilibrium, right? And that was actually the assumption we made in chapter 1, remember? We said, oh, the surface of the electrode is always in equilibrium with O and R in the electrolyte right next to it. And so if it turns out, if you go through this, you can see, I don't think I'm going to go through it because it's just a little bit of math and it's a rearranging stuff, and I'd rather spend the time on something else today in the last 5 minutes. You can see that this goes back. This will actually give you the Nernst equation in this limit. And you can go through that in your book if you want. Okay, so the last 5 minutes, I want to talk about the effects of mass transfer. Okay, so I should erase that so you can just have this in your notes. I equals I naught CO 0t over CO star e to negative alpha f beta minus CR 0t over CR star e to the 1 minus alpha f beta Okay, so we have that equation, and we want to know what happens when C star is not equal to C of 0 t. Well, we're not in these limits, right? They're both important. And we already solved this for a special case of a stirred solution with a stagnant layer, right? So if you remember, we had the electrode, and we had C of 0 t, and we had C star, and we had some concentration gradient. We could calculate the flux, right? And this was our stagnant layer. And we spent a lot of time talking about that and talking about the response, this sort of stirred voltammetry, right? Steady state stirred voltammetry, call that. And the current, I over NFA, is this equal to the mass transfer coefficient, which is d over delta, the stagnant layer thickness, diffusion coefficient, so it's just kind of like a normalized diffusion coefficient times the slope of this line, right? So the slope of that line is just given by CO star minus CO 0 t. Okay? So this is chapter 1. We did this already. This is the slope. This is essentially how good it diffuses. That gives you how much current normalized for F and A and N, right? N is the number of electrons transferred per species. And we defined this term. I can write the same equation, I over CO star MONFA equals 1 minus CO 0 t over CO star, okay? So I just divided by MO and divided by CO star, right? To get this expression. That's just the limiting current, right? So if this term goes to 0, that's the current I get when the concentration of O at the surface goes to 0. So this is just IL. So I can solve this now. I over I limiting, and this is going to be the cathodic limiting current, right? So I'm taking O and making R equals 1 minus CO 0 t over CO star. Or I could rewrite that and say CO 0 t over CO star is just equal to 1 minus I over ILC. So it's just another way to write it, but this is now being specific about the mode of mass transfer. So we just made some assumptions about the mode of mass transfer, right? We assume it conforms to this stagnant layer model. And now we can actually take this, which is, how do you figure this out, right? I mean, how do you figure out what C at the surface is in terms of stuff that you can measure, like the limiting current, which you can just measure. So that's pretty cool. So we can do the same thing for the other side. CR 0 t equal over CR star is just the same thing, equals 1 minus 1 over I L A, the anodic limiting current, and we can plug that in here.